Okay, good afternoon, everyone. Welcome to Thayer School's weekly Jones Seminar. So, Professor Brian Polk would usually introduce the speakers, but he's away today, so I have the pleasure of introducing our speakers today. Abbe Bjorklund, who's our Director of Engineering and Utilities at Dartmouth, and Steve Shadford, our Engineer Program Manager. So both of them are actually very experienced engineers, so it's a great pleasure to have them in engineering school, especially talking on a topic we are always very interested in, which is the energy status of Dartmouth College. So you can see in the title, this is about the past, present, and future of Dartmouth College energy picture. So Abbe joined us in 2015, and she oversees engineering for buildings and utilities on Dartmouth campus, as well as energy procurement, planning, and efficiency initiatives. So Steve actually joined us back in 2007 to implement the Focused Energy Efficiency Program. They are both very, very experienced engineers in building energy and utility system planning. And basically, they're going to share their experiences on how we managed to reduce the energy consumption on campus by 18% while expanding the campus by 22%. If you do some quick calculation, that's about 50% enhancement in energy efficiency. So that's a very exciting story to hear. Thanks.
Great. Thank you very much. Excuse me. Thank you very much for that introduction. It's great to be back here. I believe I did a program in 2012, about 5 years ago, when we were just really kind of getting up and going with our energy program. And at that time, we were talking about just basically the energy systems that we had here on campus and some of the big ideas that we had for heading out to use less. And we're 5 years down the road at this point, and we've accomplished an awful lot on the demand side, and we are looking very deeply at our supply side for our energy future. Abbe will take basically the kind of the deep past, the long ago past. She'll talk a little bit about Dartmouth's early innovation in energy systems way back when, and then she will fast forward to the new future, some of the ideas that we're looking at and that we've been studying for the last couple of years. And I'm going to take the middle part, and I will actually start with that, which is about pretty much the demand side of the campus and our strategic energy program, basically the genesis of that. So I'm defining basically the present as from about 2000 until just about now. This is really kind of subtitled, Striving to Use Less While Building More or Having More. It's an interesting challenge to work on. And we'll talk a little bit about the development of our strategic energy program that took place in 2007 and 2008 and show you some of the examples of the different strategies that we've employed and some of the results of the program. Because I'm sharing the podium today with Abbe, I only have half the time that I had last time, so I'm going to have to talk twice as fast. So, but anyway, these are just real quick highlights, so we'll kind of be skimming over this. Dartmouth went on a growth spurt in about the year 2000 for planning and actual development and building of a bunch of new buildings. And over a very short period of time, Dartmouth erected 6 new buildings. Some of them were in clusters, groups, and what have you. And it was a big chunk of space, about over 500,000 square feet. And it was a kind of an early foray into high-performance building design. And some of the attention to detail went into new ways of doing building envelopes and particularly different ways to handle and think about how you do mechanical systems. And we moved from basically moving lots of air around buildings for HVAC to a hydronic based system, and had some pretty good results. Some were better than others. And I just point out a couple of these buildings. One was Kemeny Haldeman, turned out to have the best results. It had a energy use index of 53,000 BTUs per square foot per year, which is pretty good in the overall picture. McLean, which is right next door, 144,000, but it's a very energy intensive building, and others in between. And overall, the average of that group of buildings came in about 72,000 BTUs per square foot. So not too bad, about a 30% improvement over what the campus average currently is, which is about 100,000 BTUs per square foot. But back in 2007, if you were a person who was responsible for planning utilities here on campus, and knowing that the campus was thinking about growing perhaps 1 million square feet over the next number of years from the beginning of this time period to somewhere around now, you might have some serious cause for concern, because there was actually not any kind of a strategic plan in place to counter the growth in energy. So what to do? The Facilities Department commissioned a strategic energy study in 2007, and the study concentrated on the 25% of the buildings that use 75% of the energy on campus. So that's about 30 buildings. They're typically the big ones: science facilities, performing arts, large academic buildings, and sports facilities. We're pretty much in that grouping. And the study identified HVAC, control system, lighting systems, and operations and maintenance opportunities that, if implemented, could have a pretty significant impact on energy utilization and kind of stem the tide of increasing energy growth on campus as newer buildings were being brought online. A master plan was developed out of that study and was adopted and launched in 2008. And we basically are now calling it our version 1.0 plan, because we're ready to launch a version 2.0 plan. And kind of looking backwards, we see that it effectively was about a 10-point plan. We didn't call it a 10-point plan back then, but it basically had 10 program elements to it. Some were sort of one-time things that needed to just get done, and other things were very, very much sort of foundational parts of it. And I will quickly march through some of these program elements and show you the results of them. The first program element is raising the bar on the high-performance design and construction. And we've done this by collaborating with our planning, design, and construction group, by setting more aggressive energy use index targets, and by supporting a highly integrated design practice, which consists of architects, engineers, specialists, Dartmouth as the owner, energy modelers, and other consultants in a sort of a continuous process from the concept of the building right through the final commissioning of the building. And one prime example of that was the Life Sciences building, which was one of the first ones that was brought online shortly after we kicked off our energy plan. And that is a 178,000 square foot building. It achieved a LEED Platinum status, and it had a target of 100,000, I think it was 99,000 BTUs per square foot per year. Very, very aggressive for a large laboratory facility. And we've actually achieved a value of 110, so pretty darn good. More recently, we built the Black Family Visual Arts Center. That has an index of about 78,000, pretty good job. And we're looking forward to a couple of new projects: the Hood Museum, which is being renovated right now and expanded, and then the Irving Institute of Energy and Society, which will be right next door. They're looking at some very, very aggressive targets, perhaps down as low as 20,000 BTUs per square foot per year, which would be pretty interesting to try to achieve. It's kind of important to have a goal to aim towards as you're doing all of this, and pretty much coincidentally, it wasn't actually part of the strategic energy plan, but coincidentally in 2008, a task force was commissioned by the then president and the provost, and a target was chosen for reductions in greenhouse gases. And it was based essentially on conservation and efficiency, not on fuel switching or supply side kinds of strategies. It was really what is sort of the art of the possible, not looking for huge silver bullets for changes. And it was sort of a three-part reduction with an overall 30% goal by 2030, with a couple of breakpoints in the middle, 20% by 2015 and 25% by 2020. So one thing to keep in mind, this is an absolute target, so it's not BTUs or something like that, or greenhouse gases per square foot. It's just absolute numbers. So the more we grow, the harder it becomes to kind of meet these objectives. So I'm just putting this up. We'll return to this graph later on in presentation so you can see how we're doing in the middle of this program. It's also kind of important to have capital to work with, and we were very fortunate to receive early endorsement and support by the trustees, and they've continued to very actively support the energy conservation and efficiency mission. We started with $12.5 million in fiscal year 2009, and established a green revolving loan fund out of those early dollars of about $1 million, and that keeps circling around, and we keep putting that back to work. And then we've had an average of about $2 million a year of commitment from the trustees moving forward. So a pretty good-sized war chest, and we've spent a good deal of that, most of it at this point, and we'll continue to ask for more and have no reason to believe that they won't be generous and provide the funds. We needed meters on the dashboard to kind of guide our plan and measure the success and our path forward. We were fortunate enough to have lots of energy meters on campus. They needed a little bit of maintenance, but we were particularly hindered by the sort of antiquated manual read method. So people would leave the heating plant once a month, go around, write numbers down in these leather books, and come back, and it was kind of a nightmare to turn it all into real information. So we fixed and we automated the 300 existing meters at that time, and later expanded to now have about 500 energy meters here on campus. We are definitely the envy of many other institutions when they see what we've accomplished and the kind of data that we can use. But the best thing about these meters really is they provide lots of data, and it really provides kind of an unvarnished view of our progress. There's kind of nowhere for us to run and hide because the meters tell the story. We also wanted an additional layer of visibility into all of the major campus energy systems, and so we ended up installing an industrial strength application. It's kind of a high-level application that sits on top of our other stuff, and it has connectors to the two major building automation systems on the campus, and into the heating and electric plant, and over into the metering systems as well. And it also has a live connection out to the web to grab weather data and projections from the NOAA website. It allows us to see multiple systems in real time and in historical time, and it's allowed us to create some really great analytics and fault detection routines. And I'm going to just show you just kind of a sample of this for one that was done and deployed for Berry Library. And we're basically grabbing a bunch of data on the HVAC control system in the building, probably over 2,000 data points. And it gets reduced down and produces a management level report, kind of telling you, summarizing what's good and what's bad. And then it provides a bunch of details that are basically actionable kinds of, it's basically a roadmap to find the needle in the haystack, to send our technicians out, and they will most likely find a smoking gun. based on these individual reports. So we've created a number of these and continue to develop them for all different types of activities. Another really great strategy that we undertook early on was the elimination of absorption cooling for the campus. It was really kind of the biggest overall opportunity that we faced. And until 2008, the campus used the absorption cooling process, which uses steam in order to make chilled water. It's thermally extremely inefficient, but it was financially viable until just about the beginning of our energy program. At that point, fuel oil became relatively higher priced, and electricity became relatively lower priced. And it kind of flipped upside down and certainly did not make, financial sense at that point. So we've since replaced 5 very large chillers, absorption chillers, with high efficiency, variable speed drive electric chillers, and we have ended up saving tremendous amounts of oil, which we'll talk about later. This is basically providing cooling to all of the large buildings up in the central, north, and south parts of the campus, not down here on the west end of the campus. That will probably be dealt with as part of the ongoing expansion down in this area. Another big opportunity has been for recovering waste exhaust air heat, particularly from laboratory buildings. Burke Chemistry, Vale Hall, and Cummings Hall each had big HVAC systems, huge 100% outdoor air systems with no heat recovery. I guess that made sense at the time they were designed financially, but it certainly no longer made sense. So we added heat recovery to the buildings, and they were very mechanically intensive and very disruptive kind of projects, but really very worth the effort. And soon we'll perform an upgrade on a system that we already have in place in Steel Hall. That's planned for later this year. So if we take strategy 5 and 6, which is the chiller replacement and the heat recovery, and we put those together, we can show you a really great example. And this was the Burke Chemistry project, where we replaced 2 very large absorption chillers with electric chillers and replaced all the airflow controls and added heat recovery to the building for the first time. And the overall results were a 64% reduction in energy use for the building, which previously was the top using energy building on the campus. And so it is now slipped down, luckily, down to number 2. And it's headed lower to maybe 3 or 4. We're currently looking at the possibility of employing a sort of a modest size, maybe 100-ton heat pump chiller at Burke to produce heating in place of steam, and all the while exporting the cooling production to our campus chill water network. And Abbe will talk a little bit more about the benefits of having these networks in place, particularly a hot water network later on. One of the foundational principles of our program really has been to retro-commission the top 30 energy-using buildings on the campus. And we've basically marched through, gotten to near the bottom of that list at this point. And it's essentially a process of retuning the buildings, putting them back to their intended methods of operations with set points and strategies. We've actually done a bunch of optimization as well through some of the operating software. It's essentially putting the wheels back on the rails where they've come off. And every building is not a disaster. Some are worse than others. But overall, it's a very positive program. It's had really good results, and running from 5 to 30% savings. And I'm just showing 2 examples here. McLean next door, we've had a 28% savings, and this is for a fairly new building built in about 2007. And then Kemeny Haldeman, about an 18% savings. So these are great. They're not heavy capital projects. It's just mostly labor and some brain power applied to them. Another key aspect of our energy program has been lighting upgrades, which we have performed for over 30 buildings on the campus. And we did this over a period of about 5 or 6 years. We have pretty much wrapped up our first round of all of this. And the projects have ranged from sort of simple replace ballasts and lamps with very high efficiency fluorescent style lighting, right up to more recently to some very high output LED fixtures that we've used for the sports venues. And wherever we've gone, we've added lighting controls as well. And the controls consist of things like occupancy sensors, daylight dimming, variable output light tuning for different spaces, and we've used touchscreen controls for some of the larger venues to provide a means for occupants, say in the sports facilities, to choose the right scenes for whatever they're doing. And overall, we've had really pretty awesome results there. Up on the screen, we're showing Berry Library, which was done in sort of 2 phases. And I think one of the cool things is that the red was the original, the blue was after the first phase, and you could see that the most energy we're using after phase 1, the sort of the top of the blue bar, is essentially at the bottom of the red. So the new high was the same as the old low. So that was pretty amazing just to start. And then we did a second phase, did a bunch of LED upgrades in that space and achieved even greater savings. So 80% nighttime savings, 45% daytime savings. And overall for the building, it's including all the fans and everything else, it was a 30% electrical reduction. That's pretty massive in the building, which is now currently our top energy user. So, and then just one other quick example. Here's a sports venue, Leverone. We installed some very large-scale LED lights in there. It's been extremely successful. You can see that it actually lights the playing area much better than the old. Old is on the top, new is on the bottom. And similar kinds of results. Whereas before, basically the lights could only be either on or off. And now each fixture, there's 120 of them, they're dimmable, they respond to daylighting. You can set different scenes, and each one has an occupancy sensor. So if nobody's playing underneath it during certain kinds of settings or scenes, the lights will actually dim down to near zero. So pretty cool stuff, and there's a lot more to come with LED lighting for the future. And then another strategy, which we're really just sort of a collaborator on, it's an effort with the Planning, Design, and Construction Department, is in building renewals. So we don't undertake those renewals directly as a facilities operation, but we have good input into setting targets, helping to set targets and raise the bar for the performance for these buildings. I'm showing an example of the Dining Commons project, which was renovated over 2 summers several years ago. It was a complete and full renovation of the building architecturally and mechanically, and it now incorporates some key energy features, including variable flow, kitchen exhaust hoods. We installed a heat recovery system for that, which is pretty uncommon in that type of an application. And we're recapturing the waste heat of the refrigeration systems in the building and using that to preheat domestic hot water and a number of other kinds of things. So overall, 40% savings for that building compared to its sort of pre-renovation performance. And just sort of footnote on that, the building was not air-conditioned before, and the 40% overall savings includes full air conditioning of the building, so pretty dramatic example. And our last kind of simple example here of something that's just very easy to do is some preventive maintenance kind of work, and this is an example of a steam trap, and we instituted a maintenance program for that. For the entire steam system. We inspected with an outside service, over 2,000 steam traps, found about a 6% leakage rate, which wasn't too bad. But when it's all added up and fixed, it resulted in a $250,000 a year savings. So something that's very important to do. And so we've basically instituted a continuous program now where we will do this every 2 or 3 years. We did it for a second time relatively recently, and the second time through it was a 2% failure rate. So that's a good thing. It shows staying on top of it makes good financial sense. So how have we done? We think we've done pretty well. We're very pleased with the results at this point, and using the common base of the greenhouse gas reduction pledge, which is a base of the year 2005, we have dropped our use of fuel oil by almost 2 million gallons per year, so 36%. And I'm just using these numbers. This is not normalized. This is just the numbers that we had in 2005 and the most recent data we had for 2016. So I suppose if we normalize that, it wouldn't be quite as dramatic as that, but it would be nearly as dramatic as that. And this is all, overall, we've reduced our energy consumption on campus because electricity has gone up with the addition of all of these buildings. And we're using electricity to drive chillers now and all. But overall, total energy reduction has dropped by 24% in that same time period. And the gross square footage on the campus has increased by 19%, so almost 25%. It should be emphasized that the savings really come as a result of a big collective effort that's going on. So it's not, we can't say that the energy program is taking responsibility for this. It's really a big collaboration between the energy program, the capital renewal activities and programs that take place on campus, the new construction, building good new buildings, and improved operations on campus. But if you add that all up, we've had a pretty good impact. And here we can just see the same thing graphically. So the red is square footage going upward, and the blue is energy use going downward. And if you see the little graph in the upper right-hand corner, that was kind of the starting point question of like, well, if we keep on building this 1 million square feet, what's going to happen? Energy is going to go out of sight. And as you can see, energy's actually turned around and gone just the other way. So that's what we're trying to do. Back to the greenhouse gas chart, just kind of like, well, where are we on our targets here? And this shows that we were able to meet and to exceed the 20% reduction goal in 2015. The numbers for fiscal year 16 are being cranked out right now in the sustainability office. They are punching up those numbers. I think they will be similar to where we were the previous year, if not slightly better. So I think we're still on this sort of downward trend, which is really good. The road gets harder the further we go out to the right because it's just whatever. It's just harder to do this stuff. But we're not out of ideas, and we are definitely not out of ambition to do the right job. So currently we're developing an updated strategic energy plan, which we're calling Energy Efficiency 2.0. And you'll see happens to be 10 things. It could be 20 by the time we're done. It's everything is not a 10-point plan, but I just came up with sort of 10 of the most key things. The bold black ones are things that we can kind of continue doing or jump into and do over the relatively short run. And the red and the blue thing is really more of a supply side activity, which Abby's going to talk much more about in her talk. But it also affects the demand side as well by converting the campus to a district hot water system and connecting chiller plants together, which we haven't really talked about yet, but Abbe will cover that. At that point, we'll have the ability to exchange energy from one source to another through heat pump systems. So it will be pretty cool if we can get to that place. So we're not out of bullets, and that's pretty much where we are at this point. And I'm going to turn it over to Abbe, who will briefly take you into the past.
Thanks, Steve. So, as Steve said, he was talking more about all the efforts we've had over the past 10 years to reduce our energy demands on campus. And I'm going to be talking more about ways that we can work to reduce our supply, and by that I mean the energy and greenhouse gases we use to supply heat, supply cooling, and supply electricity to the campus. So Dartmouth was a very early energy system innovator. In fact, Dartmouth was the first campus on the East Coast to build a district energy system back in 1898. And we still actually have that same central heating plant, which we've renovated over the years. That plant originally burned coal, and in 1905 we implemented another innovation, which was to install steam reciprocating engines to co-generate electricity on the campus as well. And at that time, it was actually generating DC electricity, distributing DC. In 1922, we switched from burning coal to oil, number 6 oil, which at that time was also an innovation. We were a pretty early adopter of this new thing called oil. But in the past 100 years or so, we've pretty much been doing the same thing. We're still generating steam. We're still burning oil in our heating plant. And so is it time for us to think about some changes? How many of you have toured our campus heating plant? I would highly encourage you to do that. You can actually sign up for a tour right on our website, the Dartmouth website. And it is a really great plant. It's very well run, very efficiently run for the technology that it is. But due to the nature of steam technology, we're actually, due to the plant efficiency and the distribution system efficiency, we're losing about 40% of the available energy in our fuel before it gets out to our buildings and gets used for heating. We also have a very old steam distribution system, and steam distribution is very expensive to operate and maintain. And due to the age of the system, we're estimating that we'll need to spend about $61 million over the next 30 years in today's dollars to maintain and replace portions of that system as needed. So Steve had showed you our greenhouse gas reduction targets, and for this graph, I'm showing the full area under the curve there. So our goal that was set by President Wright back in 2008 was a 30% reduction by 2030. But that other 70% is another opportunity for us for reducing our greenhouse gases. And as you can see from the pie chart on the right, most of the greenhouse gases, this is scope 1 and 2 greenhouse gases for our campus, are associated with burning number 6 oil and with our electricity purchases. So that's an area for us to focus when we want to reduce greenhouse gases for the campus. So the campus has looked at many options to switch from number 6 oil for our heating plant. We've looked at going to number 2 oil, which would require minimal capital investment. It would improve our operations. It's easier to work with number 2 oil than number 6 in terms of operating boilers. But our carbon emissions would only be reduced by a fraction of a percent, and our fuel costs would increase by about 30%. So not a great option. We've looked at liquefied natural gas and compressed natural gas options for the campus as well. You may be aware that Dartmouth Hitchcock Hospital currently utilizes, I think it's LNG, or is it CNG? CNG. And they have to ship in containers of gas into their campus. It would require a significant capital investment for us to convert to LNG or CNG. It would be about 20% less costly than burning number 6 oil, not including those capital costs. And it would reduce our carbon emissions by about 30% due to the nature of natural gas, greenhouse gas emissions compared to oil. But we'd still be burning fossil fuels. It would not be a renewable energy resource. We've also been investigating biodiesel as an option as a fuel for our campus. We're currently restricted by the New Hampshire DES in the amount of biodiesel that we could burn in our facility because we have a Title V permit. We're a major source emitter. There is legislation in front of the state of New Hampshire that we are hoping will get passed soon, and that will make that restriction go away. The biodiesel would be similar to number 6 fuel oil in that the fuel costs would be higher, the capital costs would be negligible, and the O&M costs would be lower. But the carbon emissions reductions would be significantly greater, and it really depends on how much biodiesel we would be able to burn. It could be 10 to 75% carbon emissions reduction in the plant to burn biodiesel. We've also looked at biomass wood chips as an option for our existing plant, and similar greenhouse gas reduction impact of burning biomass to biodiesel, but we have very limited space. If any of you who have been to the plant know that it's right downtown, right adjacent to downtown, and biomass wood chips require a lot of space for fuel storage and handling and delivery, and we really don't have that for the existing plant. So over the past 2 years, Dartmouth has taken a step back to ask the question, if we were starting from scratch, what are the best energy technologies and systems that we could be using to meet our energy needs on our campus? And what should we be working towards? So we have, with the support of our Board of Trustees, we've embarked on a series of scoping studies and detailed studies of different energy technologies for our campus. We decided to bring in a consultant from Denmark. As many of you know, Denmark is really a world leader in energy technology and energy engineering. And we've been working with a consultant called Ramboll, and they did some scoping studies for us and evaluated several options for cost savings and greenhouse gas reduction for our campus. We've also done several follow-up detailed studies of some selected technologies, and we've looked at, from a life cycle cost point of view, how would the cost of building, owning, and operating those systems compare to continuing on with our current business as usual, in other words, burning oil and maintaining our steam generation and distribution systems. So there have been several considerations for these studies. We want to look for ways that we can mitigate risk associated with our dependence on number 6 oil. There's a lot of price volatility in oil due to the nature of where oil is coming from in the world. So we're very interested in how can we be more diverse and more resilient in our fuel supply. We want to reduce our energy and our O&M expenditures, which are close to $15 million a year that Dartmouth spends on procuring fuel and electricity and maintaining our energy systems. We want to look for how can we intelligently modernize and invest in our energy infrastructure, and also to reestablish Dartmouth as a leader in energy. As I said 100 years ago, Dartmouth was an innovator for energy. I think many of you are involved in very innovative energy research here on campus. So how can we also be a leader in the way that we utilize energy on our campus? And in the process of doing that, provide some experiential learning and research opportunities to our faculty and our students. And finally, how can we convert to renewable energy resources and in the process reduce our greenhouse gas emissions and improve our energy supply chain and have more positive impact and control on where our fuel is sourced? So working with Ramboll, we pretty quickly identified that biomass was an excellent fuel option for our campus. It would result in a 75% reduction in our plant carbon emissions and our fuel costs. And that's assuming EPA biogenic carbon accounting. Realistically, it would require building a new plant at a location that's off campus or adjacent to the campus. Again, going back to the issues I was talking about of needing space for biomass systems. It would give us an opportunity to really help to develop and support our wood chip industry in the area. We determined that there's an adequate wood chip availability within 50 to 75 miles of the campus. And by being a major procurer of those wood chips, we could help to develop a sustainably forested supply market in our region and utilize locally sourced renewable energy to fuel our campus. Also, another benefit would be in terms of our permitting with the state, we would go from a major source emitter to a minor source emitter. Working with Ramboll, we also identified the benefits of converting our steam distribution system to a hot water distribution system, and in particular, what I call a European-style low temperature, high delta T hot water distribution, which in terms of construction costs a third or less of what it costs to install steam distribution. Also has much lower heat losses, about 4% versus the 15 to 20% that we have from our steam system. And maintenance is much easier, shorter installation times, less disruption for the campus. It would require that we convert our building systems from steam to hot water, and I'll talk a little more about that later in the presentation, but the advantages of that are improved comfort, efficiency, and control. Also, with hot water, we can store energy, so it allows us to be much more innovative in the way that we control and manage our heating loads on campus. And we can easily integrate alternative energy technologies. Steve mentioned heat pumps. We could integrate solar thermal, we could integrate geothermal fuel cells, or all sorts of innovative technologies that our professors and students might be studying and researching. As part of our work, we've been looking at what are our peers doing, both nationally and internationally, and You may have heard that out on the West Coast, both Stanford University and the University of British Columbia converted to European-style hot water distribution systems a couple of years ago. And we've studied those systems very closely and conferred with our colleagues at those institutions about their process and their lessons learned and how we might be able to apply them here at our campus. The University of Rochester in New York has also been converting their system to hot water. Some of our other peers, such as Cornell, Princeton, and MIT, are studying ways to convert their campuses to hot water distribution. Also, many of our peers here in northern New England in particular that are away from gas pipelines have converted their campuses to biomass from their central plants. With Ramboll, we've also looked at many other technology options for our campus, including large-scale solar thermal combined with seasonal thermal storage, which is something that has been implemented extensively in Denmark, large-scale heat pumps, aquifer thermal energy storage, and organic Rankine cycle technology, which is a cogeneration technology, ground source heat pumps, among other technologies. So the result of this has been that we've developed a vision of where we could bring the campus that is renewable, modular, flexible, and resilient. It starts first with the kind of work that Steve has been talking about, our Energy Efficiency 2.0, which is to continue our efforts to improve the efficiency of our existing facilities and to design and build and operate high-performance new buildings on our campus. We're recommending that we install a hot water distribution system that would incorporate hot water thermal storage capability. In conjunction with that, we would be converting the heating systems in our buildings that don't already utilize hot water from steam to hot water distribution in the buildings. We could incorporate cogeneration, in particular organic Rankine cycle technology, into that biomass heating plant, and also provide a portion of our electricity. And we would be sourcing locally sourced, sustainably harvested biomass as our primary fuel for that heating plant. We're also proposing to connect our district cooling systems together. We have a number of regional chiller plants on our campus. On the north end of campus, we have a large chiller plant. We also have chiller plants in the med school and our south chiller plant in the arts district, as well as some chiller plants here on the west end of campus. So by interconnecting those plants together, it will allow us to operate those systems as an integrated system, which will have a lot of advantages. Number one, it means that we can use the capacity that we already have to serve future cooling loads on the campus, for example, new buildings or renovations to existing buildings. And it would also allow us to operate the system overall more efficiently by deploying the most efficient resources that we have to meet those cooling loads. As we need to add more capacity to those systems as cooling loads grow on the campus, we would add thermal energy storage, diurnal thermal energy storage, chill water storage, as well as potentially seasonal storage to that system in the future. And as we need to replace our existing cooling assets, we would propose to install heat pump chillers that could transfer heat from our heating loop to our cooling loop, or I guess take the heat from our chillers and put it into our heating loop, depending on how you want to describe it. But as Steve suggested, having our chilled water distribution throughout the campus and our hot water distribution gives us much more flexibility in a way to move heat from one application to another on our campus. We also are proposing that we add more renewable generation options to our campus, including solar PV for generating electricity, and solar thermal systems could be added, as I said, to our thermal network to provide hot water. So tying it all together, this system will not only be more renewable and flexible and resilient, but will provide some experiential learning opportunities that can be really a living laboratory concept for our students and our faculty. This new energy system would also prepare Dartmouth for our change in electric marketplace, where time of use pricing with much higher built-in capacity charges is going to increase the overall cost of electricity. So this integrated energy system will allow us to manage energy in a way that we never could before to minimize our energy costs. We did a 30-year life cycle cost analysis comparing different options. This chart compares the business as usual case, which is scenario 1. So this would be our cost over the next 30 years to basically continue with our current steam system. The purple is O&M, the blue is electric and fuel costs, the green is capital costs. So under that scenario, we have low capital costs, relatively low capital costs, but very high fuel costs and O&M costs. Scenario 2 would be if we just installed our hot water distribution system and converted our buildings, we'd have about a 20% drop in our fuel costs and O&M costs, a increase in our capital costs, about a 20% drop in our greenhouse gases. Scenario 3 would be to also build a new biomass plant, which would significantly reduce our fuel costs and our O&M costs by about 75%, and our greenhouse gases would also be reduced, just associated with our plant, by over 50%. Scenario 4 would be the biomass plant that also integrates ORC cogeneration technology. So for as many of you know who have done life cycle cost analysis, there's a lot of assumptions behind this analysis in terms of discount rates, inflation rates, what's the time frame of the implementation of these changes. But we've done a lot of tweaking of these numbers, looking at different scenarios, and I think the main takeaway is overall the net present value is about the same, whether we continue with our business as usual now or we go to the more renewable, resilient option. But the advantage of the more renewable, resilient is that we're also significantly reducing our greenhouse gas impact. So going back to some of the considerations I talked about at the beginning, we also, this chart really just compares these same 4 scenarios. Scenario 1, the business as usual, has the lowest capital cost, the lowest construction impact, but we're really not meeting any of our other goals in terms of carbon reduction, system efficiency, energy price volatility, or O&M cost reduction. Scenario 2, where we have an increased capital cost and construction costs. We've reduced our energy requirements by about 20% and our O&M costs, but we're still burning oil. Scenario 3 and Scenario 4, with the biomass hot water conversions, we have our highest capital costs, but we're meeting our other goals in terms of reducing our carbon footprint, reducing our operating costs, and our associated energy supply chain impact. So, as I said, to convert to hot water distribution on our campus, that means doing a lot of work in our buildings. The blue buildings are the hybrid buildings, so these ones have kind of a combination of steam and hot water systems in these buildings. The red buildings are the all-steam systems, and the green are already hot water. So as you can see, we have a lot of work to do to transform our energy systems in our buildings. But it's also an opportunity for renewal and improvement in those buildings. We actually just this past summer converted our Bartlett Hall building from steam to hot water. Does anybody here work in that building? Well, I had the opportunity to meet with the occupants of the building this past winter, and I can report back that they're very happy with the changes in terms of comfort improvements. And the system is operating very well. It's very low temperature and high delta T, and we're in the process now of planning more building conversions as we renovate the buildings. So this shows the greenhouse gas reduction if we did the biomass and hot water conversion. And as you can see, we're cutting way down into that area under the curve, much lower than we had just from our energy efficiency improvements on our existing facilities. So the greenhouse gas reductions would be even lower if we incorporate additional things like implementing photovoltaics and other technologies on our campus. So what are our next steps? We're working with the campus administration to develop a timeline and look at funding options for implementing these changes and planning our campus energy transformation. We are also putting together plans and starting to implement our energy efficiency 2.0 in existing facilities. We're also working very closely with our consultants and our planning, design, and construction department on designing high-performance buildings. For example, as Steve mentioned, the new Institute for Energy and Society building will be our lowest energy building, probably 15 to 20,000 BTUs per square foot per year. We're also starting to embark on implementing solar PV. We have a couple of solar PV installations planned for this summer on campus, and we're also studying a potential for a very large solar PV installation that would make a major impact on our campus electric greenhouse gas reduction. We're also collaborating with the town of Hanover. Many of you may be aware that there is going to be a vote at the town meeting coming up in a couple weeks for the Ready for 100 renewable energy goals. And we anticipate working very closely with the town on our mutual goals to reduce our greenhouse gases. We are now starting to plan the interconnection of our campus chill water plants on campus, and we are integrating hot water conversion into our projects. So, for example, the Hood project that's under construction now will be installing our first section of hot water distribution in conjunction with that project. And we're also starting to plan other hot water distribution projects around the campus. So that's the end of our presentation, and Steve and I would be more than happy to answer any questions that you might have.
You did not mention wind energy. What's the idea considered at all?
Rosie, you want to answer that?
Sure. We have looked at wind in a variety of forms. I'm working for as director of sustainability, and I have the pleasure of working with Abbe and Steve while we're leading the heavy lifting. We've looked at wind energy projects over the years, and
But it is an option that we'll be continually to consider in the future as we want to increase the sustainability of our electric resources.
So I'm really excited about this because it sounds to me like there's an open opportunity to add more renewable solar or wind as it does become viable. Batteries, battery storage, all of that is still possible with this plan, and biomass seems like it is the most reasonable because we have that resource as long as we know we're using it, sustainably. That it's a great plan. I just wish we could do it now. Sooner than later.
I have a question for each of you, if I may.
Sure.
On the financial projections, one thing I noticed down at the bottom is there was a negative bar for renewable energy credits sold.
Mm-hmm.
And that sounds like a good way to make it viable, but I'm wondering how that's factored into the CO2 reduction calculation.
Well, I think that it's probably unlikely that we would sell renewable energy credits because we want to be able to own the renewable energy credits. And in fact, for those PV projects that I mentioned that we're planning for this summer, Dartmouth will own the RECs for those projects. But we're still, economically, the numbers are quite good. In fact, we're going to be purchasing those systems through PPAs at a cost that's less than or equal to what we're spending to procure electricity now. So the market is such just, because through PPA, the developers can take advantage of tax credits. We are also getting some rebates from the state as well for PV. So, that would be something that would help with the finances a little bit, but I don't think we're going to do that.
Great. And my question for Steve, if I may, is you talked about a huge number of different kinds of work that your office does. I'm curious how much of that is done by staff, by Dartmouth staff, your staff, and FOM staff, and how much you hire outside contractors to do.
Okay, well, that's a great question. We actually have a pretty small staff. The staff is kind of expanded beyond just my immediate kind of energy group, which is me and an energy analyst. We used to have a person working full-time on lighting. He has since retired, and so our lighting program is sort of getting ready to start over again. Just good timing for that. But we also reach into our engineering group, which we're all part of the engineering group after all. So we have a mechanical engineer, and a junior mechanical engineer, and an electrical engineer. So between all of us, there's a lot of collaboration on the whole range of these kinds of things. I mean, we've covered a lot of ground this afternoon. We do employ the services of outside consultants, and we've had a firm that works with colleges and universities help us particularly on the retro-commissioning work, on doing the evaluative studies for that, and then essentially it's sort of the general contracting to manage contractors, particularly control contractors and maybe some mechanical contractors to achieve some of the results for the retro-commissioning program. And then some of the larger activities that I referenced, such as the huge work that was done at the Burke Chemistry building, that was essentially a capital renewal project because everything was pretty much old and antiquated. I mean, we employed all new technologies and new approaches to it, but that was done in a more traditional way so that it essentially was outsourced. There was a construction manager who came in near the end of the design phase. There was a mechanical and electrical engineering firm that did all of the design work for that. And so it ran through and had a whole commissioning process, et cetera. Looks more like building a new building kind of a thing. So a big chunk of our money went to that. The first $12 million or $11 million went to that. We spent it all in one place, but it was a great place to start. So I don't know if I fully answered your question, but we spread it around. It really depends. I guess the one theme that we've had is on the retro commissioning programs we have used some outside services people. But we meet every week, small team of people, just to stay on track of this stuff and move it through year after year.
Can you talk about the biomass saving options that we looked at and where you think that might end up?
We have looked at some different options, and that's still being considered by the campus administration.
Well, yes, it was the way that things were done 100 years ago. It was a great way. Steam has a very high impact. You can pack a lot of energy into a relatively small pipe. And so it was kind of a great way to do things. But it turns out that it's relatively inefficient in terms of running a steam plant, and then the losses that you have, because it's at a much higher temperature than hot water. Tremendously higher temperature. We're actually lucky to have a kind of a low pressure distribution system, so that's not so hot. But some campuses have, they're sending 150 pound steam around at, 350 degrees or something like that. So you can imagine the losses in insulation. But there's a lot of losses in the plant that are associated, just parasitic losses associated with having a steam plant, heating the fuel oil, using steam to atomize the fuel oil. The makeup water, continuously blowing down steam and all of that. The organic Rankine cycle that Abbe put up on the screen, it's not a new technology, but it's been relatively perfected at the scale that we would use it here on our campus, kind of the sort of 2 megawatt modular size by an Italian firm called Turboden. And they've put a number of these systems out into sort of small district heating systems throughout Europe. So the beauty of that is entirely closed system. There is no makeup, so there are no losses associated with it that we have from the steam system. So many campuses are considering the same types of or having the same types of concerns that we have. We just went to a conference within the last month or so, and it was amazing. One of the common themes was conversion to hot water. So we were kind of like pretty far ahead of the curve on our thinking, and it was amazing how many colleges and universities are thinking about doing the same thing. But the big problem is just kind of the investment that's in the kind of the built infrastructure already and the disruption to it. So, but we think we have a plan. Yeah. Yep.
Yes. Thank you for the clear and informative presentation. I have a comment, a question and a comment, and it follows this gentleman's question about siting of a possible biomass plant. My question is how big a footprint, how much acreage you need for that, how close to the place where it's going to be utilized you need to locate this. And then the comment is that real estate's a little bit tight in Hanover, if you may have noticed. And Dartmouth has a heating plant, and I'm wondering whether, if the heating plant had to go, whether the college might consider talking and collaborating with the town in advance and maybe putting an indoor practice facility on that particular footprint and collaborate in a way that would probably make for good neighborliness. But I don't want to address that question, but the other more specific is how close does it need to be? Can it be at Sachem Village? Can it be out at where the DPW, town DPW located? Can it be in Etna? Those kind of questions. Thank you.
Well, the nice thing, as I said, about the hot water technology is that the losses are quite low in the distribution. So we could be a couple miles out from campus, but the issue is the further you go, the more expensive it is to do the installation. And we have looked at options fairly far from campus, a couple miles out. And you're right, if we decommissioned our existing plant, it would free up some, probably about, 2 acres or something? And as far as the size of the biomass plant, I think we're estimating about 4 acres.
Yeah, it's not huge.
Thank you.
Yeah.
Very quick question. Would the chilled water go into the same distribution system as the hot water, just at a different time of year?
No, we actually, we would maintain both systems in parallel because we're always doing some cooling and some heating on the campus. And if we're utilizing heat pumps, we would probably be doing more of that, but more efficiently.